Building an industrial automation sequence requires precise control over time. Our challenge today is to automate a multi-step manufacturing process from start to finish, relying on just a single sensor to trigger the entire operation. We will use a paint spring booth as our example. When a part enters the booth, our system must execute 3 distinct stages in order: paint the object, dry the object, and finally, eject the object. This animated timeline tracks the precise 22-second execution required for success. First, an orange spray phase lasting exactly 10 seconds. Second, a 10-second drying phase powered by fans. Finally, a puncher mechanism engages for 2 seconds to push the completed object down the line. By the end of this exercise, you will know how to program and virtually simulate this exact timing sequence using ladder logic. To follow along, you will need access to Siemens TIA Portal, specifically version 16 or later. Once you build and control a strict 22-second cascade like this, you have the logic structure needed to automate almost any time-based manufacturing process. Step 1 is mapping our physical hardware to the PLC's internal memory. In TIA Portal, navigate to your PLC tags and open the default tag table. Here, we define the starting conditions. Add 2 inputs to the table, one for the manual start button and one for the sensor that detects when a part enters the booth. Looking at the TIA Portal tag table interface, we now map our physical outputs. Pay close attention to the highlighted address column. The spray nozzle, drying fans, and puncher must all be designated with a Q address, starting with Q0.0, to tell the PLC these are outward actions. Strictly separating your I inputs from your Q outputs in this table prevents logic routing failures before you even draw your first rung. Move to the main OB1 block to draw our ladder diagram. Start network 1 by inserting a normally open contact for the start button, wired in series with a normally open contact for the sensor. These trigger our first output, the spray nozzle. To keep that nozzle on for the required duration, we attach a TP or pulse timer to the coil. This logical timing graph demonstrates exactly why we chose a pulse timer. Even if the sensor input is a brief spike as the object rolls past, the TP timer output holds the signal steady for the full 10 seconds we specify in the preset value. With the spray phase programmed, move down to network 2 to set up the drying fans. We want the fans to start the exact moment the spray stops. To do this, we use a normally closed contact linked to the spray nozzle. When the spray timer finishes and turns off, the switch snaps back to its closed position, instantly sending power to the next block. This initiates our second TP timer, preset to 10 seconds, keeping the drying fans running. Linking a normally closed contact to the previous step's output is the most reliable way to chain sequential actions without requiring a human operator to push another button. Finally, we build the third branch to control the puncher mechanism. For this stage, we introduce the TON, or on-delay timer. This comparison shows the difference. While the TP timer fires its output during the timing phase, the TON timer forces the output to wait blankly, firing a spike only after the time elapses. We set the TON timer's preset value to exactly 20 seconds. This accounts for the 10 seconds of spraying plus the 10 seconds of drying. Once those 20 seconds expire, the TON timer allows power to flow into one final TP timer. We set this last TP timer to 2 seconds, which physically activates the puncher to clear the booth. In this compound logic structure, the TON timer serves as the schedule, keeping the puncher waiting in the wings, while the final TP timer dictates the actual physical duration of the punch. Before we test this on physical machinery, we verify the logic. Click Load, finish the compile, and then start the virtual CPU to begin monitoring. Looking at the PLC Sim interface, you must complete one critical step to avoid a simulation failure. Right-click in the simulation table and click the Load Project Tags icon, indicated by the arrow. This bridges your code with the simulator. Let's run a safety check. Turn on the Start button alone. The spray nozzle remains off because the logical condition requires the sensor to be active as well. Now activate the sensor to simulate a part entering the booth and watch the cascade begin. Watch the abstract ladder logic flow. The green power line holds the first rung for 10 seconds of spray. It drops to the second rung for 10 seconds of fan drying.
Finally, it drops to the third rung, flashing the puncher for a 2-second burst. Running this simulation in PLC Sim confirms our logic is sound, preventing expensive timing collisions on the actual factory floor. You have now successfully engineered a fully automated, continuous 22-second production sequence from a single input trigger. To build it, we used the distinct behaviors of 2 timers: the TP timer to control how long an action occurs, and the TON timer to control exactly when an action is allowed to start. We chained those timed events together cleanly by using normally closed contacts to detect when the previous machine had safely powered down. Now, try to expand this logic on your own. Your challenge is to add an emergency stop button to your tag table and wire it into your ladder logic so that pressing it instantly resets all 3 timers to 0. Understanding how to manipulate timers and contacts gives you the control needed to turn basic code into reliable industrial automation.